afternoon all. So today we will look at the basics of computing, because this course is about introduction to computing. You should get an idea of what computing means, right? So like we discussed in the last class, computer science is the science of computing, right? So let's get into the content. So the only language a computer actually understands is that of bits. You all know bits and bytes, or most of you know bits and bytes. Like when you discuss, like when you are buying a computer, you may ask what is the size of the RAM or CPU, what is the processing power of a CPU, or what is the size of hard disk, right? All these things. So nowadays, minimum RAM is like 8 GB, 16 GB, and so on, and hard disk is minimum 500 GB, 1 TB, and so on, right? So what are these? What is a GB? Gigabyte, right? And when we say gigabyte, how many bytes does it mean? 1024 bytes. 10 to the power of 9. Any other answers? Gigabyte consists of how many bytes? 12. Yeah? 10 to the power of 9. Any other answers? 10 power? Yeah. 10 power 6, someone said. Okay. Any other answers? Okay. And what does a byte mean?
A 0 byte, it's the basic unit, sir.
0 or 1. Okay. Yeah.
So it's like the basic unit, no?
Basic unit. Okay. Have you heard of bits?
Yes.
So what is the relation between the bit and byte? 8 bits make 1 byte, right? So bit is a more basic unit than byte. Bit is the most basic unit. Okay, byte itself can be broken down into bits, right? So 1 byte consists of 8 bits. And how many bytes make up a kilobyte? Yeah? 1024, right? 1 KB is 1024 bytes. Okay? And then 1 MB is 1024 kilobytes. 1 GB is 1024 megabytes. MB means megabytes. Okay? So whatever terms you hear of GB, MB, KB, they are all made up of bits. Okay? Finally, everything boils down to bits. So 8 bits make up a byte. 1024 bytes make up a kilobyte. 1024 kilobytes make up a megabyte, and 1024 megabytes make up a gigabyte. And then you have terabytes and so on. Okay? So this keeps on going, but the fundamental unit is bit. And bit comes from the words binary digits. Okay? Bit is nothing but a short form of binary digit. So what are the binary digits? 0 and 1. Right? And why 0 and 1? Why not 2 and 3 or 5 and 7? Why 0 and 1? Yeah, someone?
Sir, I think it has a relation to like Morse code and like that. If like the 0 is a tap,
On and
like
off.
2 taps.
Right. Yeah, why only zeros? How does the computer understand only zeros and ones? Is it born with that? Yeah?
Zero means on and off, right? Like they mean
Yes, sir, 0 and 1. So like 0 it means off and 1 on, and so with that combination of 0 and 1 we can make certain different.
Yeah, you see, you need to get to the basics. A computer is nothing but an electronic device, and it's made up of electronic circuits. And how do you operate an electronic circuit? By passing electricity through it. That's it. So it only electrical signals on and off. That's it. This concept of 0 and 1 is also only for us humans. Computer doesn't know 0 and 1. It's binary. Binary means two things. So the only two things it understands in its language is on and off. That's it. We are calling off as 0 and on as 1. Okay? So computer actually understands only on and off. But rather than using these terms on and off, we are using the terms 1 and 0. Okay? So when we say computer understands only zeros and ones, it means computer understands only on and off or low voltage and high voltage. Okay? So these are the only two things that a computer understands. So everything you do with a computer finally has to boil down to these electrical signals. That's all, nothing else. Okay? Alright, so the only language a computer actually understands is that of bits. To understand why so, we need to understand the high level architecture of a computer. So most of you might be knowing this, or some of you might not be knowing this, von Neumann architecture, right? So a computer basically has CPU, input devices, output devices. Alright, so CPU, the processing unit, apart from CPU, we also have storage. Okay, so within CPU, so this is the CPU module. All right, so within CPU you have control unit, arithmetic and logic unit, and then registers. Registers are also storage, but very small storage, but very fast access. Okay, they are very close to the CPU, so that information can be sent back and forth extremely fast through registers. And then you have something called main memory. So what is main memory?
So it's like RAM and also this is the main memory, sir, which is used to like access.
Yeah.
So secondary memory is like sir the storage things where we store like hard disk or SSD.
Exactly. So main memory is what we call as RAM. So when you say 8 GB RAM, 16 GB RAM, so that is main memory. Okay, that is temporary memory. When you switch off the computer, whatever is there in the RAM, that disappears. But if you want to store the data even when your computer is off, what do you use? Secondary memory. Those are hard disks, right? So main memory is RAM, secondary memory is hard disk. And registers are also memory, but they're extremely fast. So you can think of it like different levels. Registers are the most, they're extremely fast. And then RAM is faster, not faster. RAM comes next to registers in terms of speed. And then hard disk is slightly slower compared to RAM and registers. Okay? So each one has its own trade-off, right? RAM is more costly because it is faster, but it is temporary, right? Hard disk memory is like permanent. I mean, technically nothing is permanent. It will fade off after some time. Even if you don't do anything, the disks will fade off. Okay, the content of the disks will fade off. So, but generally speaking, hard disk stores the data until you erase it. Okay, so in that sense, hard disk memory is permanent, whereas RAM's memory is temporary, and registers memory is also temporary. Okay, but registers are extremely fast, then RAM, then hard disk. Okay, so this is CPU and storage. All right, and input devices and output devices, we know basic regular input devices which we use are keyboard and mouse, right? Output devices are like display and printer. All right, can you think of any other input devices? Microphone, yes. Sorry?
Controller.
Biometric device, yeah.
Controller.
Controller, like what?
Like a console controller.
Console, yes, yes. Sorry? Camera, yes. Huh? Pen drive, it's not input. It's a storage device. It's like you attach a storage device externally. Like you are attaching hard disk, you can also attach external hard disk. Similarly, pen drive also you can attach. Okay, what else?
The tablets, drawing tablets.
Yes, tablet, digital tablet, yeah. Yes, microphone, someone said already, yeah. Stylus, yeah. Digital tablet comes with a stylus, yeah. Joystick, yeah. Yeah, touchpad is also an input device, yes. What about any other output devices? What else? Okay, so we'll just look at them in a couple of slides. All right, so this is like a more simplistic view of a computer. So basically you have input devices and output devices, and in between you have processing and storage devices. Okay, so that's it. That's like the high level view of a computer. All right, so you have a processor and you have storage, and you get input from somewhere into this processor and storage. You do some processing, you do some computing, and output something. Okay, so like this is what we, if you recollect in yesterday's class, this is what we saw as the definition of computing, right? To come together, to sort of to settle together. That is, you can have one or more inputs, and you do something with those inputs, and you settle at an output. Okay, so whatever happens inside a computer right now, we are not worried about that, but a computer takes inputs and gives you an output. That's all. So that is the high level view of a computer. Okay, so these are all various input devices, right? Mouse, keyboard, joystick, light pen, that's like stylus, scanner. Scanner is another input device. Trackball, camera, touchpad, microphone. Okay, yeah, and these are images of primary memory and secondary memory, right? So RAM and hard disks. This is primary memory, that is secondary memory. And processor looks somewhat like this. And these are all various output devices. Almost everything is covered except plotter. There is also like a printer. Okay, yeah. So you know most of these things. Okay, all right. Now if you look at the process of the flow of data, so initially the data comes either from the input device or from the memory, that is the storage, or both, right? Usually at least some input has to come from the input device, right? Even for the CPU to access the memory and do something, we have to give an instruction to the CPU to do that. So that instruction has to go through some input device, right? Like I may say read a file, but it won't read a file until I tell that, right? So I tell it to read a file either through keyboard or mouse. When I double click a file, it opens that file. It accesses that storage and opens that file, right? So I need to at least give input through mouse or keyboard or whatever it is. Okay, so if you look at this diagram, you look at these dots. Okay, so this is the information. The information is flowing from the input device as well as from the storage into the CPU. Okay, so information is coming from both places, and then the CPU uses this input, does some processing, and gives an output. So these are the these dots represent the output information. Not yet output, it's not sent to the output, but it is just processing. It is temporary output. You can think of it as temporary output. So it may need many steps to compute the information. Suppose if I give it a large Excel file and if I ask it to sort it, it may need to go through that Excel file multiple times. Okay, so it may need to access the storage multiple times and write to the storage, right? So I may ask it to just write to the storage, need not display to me, or I may ask it to both write to the storage as well as display the output to me. So I can ask it to do anything, right? So here input is coming from the storage and output is being written back to the storage. But if I also ask it to show me the output, then the output is displayed through some output device. It can be monitor, it can be projector, whatever it is, it displays that information through the output device. Okay, quite simple. You take input, process it, give me the output. That's it, right? Okay, now all this is a high level view of computer. So we don't know what's happening inside a computer, right? It's being looked at as a black box. All that I'm seeing is I'm giving an input, I'm getting an output. How a computer is doing it, I don't know. Okay, so that's what we are going to get into now. So again, at a high level view, what a computer is doing is it is executing a series of commands. It is implementing an algorithm. Okay, so you tell the steps which the computer needs to follow to process the input to get the desired output, right? I may give some input, I may give a list of names. I may want the computer to do different things. I may want it to just sort those names, so that is one kind of, it may require one kind of algorithm for that, or I may just ask the computer to just count the names, how many names are there in this list. It will need to follow different steps for that. Or I may ask the computer to just concatenate all these names, right, as into one string, right? Or I may ask it to delete some names or delete some duplicates from it, right? So these are all different tasks that I am giving the computer to do. So data is one, but the tasks are different. The algorithm will be different for different tasks. All right. So that is what an algorithm means. Algorithm just means some sequence of steps. As simple as that. So we give that algorithm to the computer and it executes those steps. Okay. So as an example, you can think of some very simple example, add operation. To add two numbers and store it in a third number, or to add two variables and to store it in third variable. These are the sequence of steps. This is like a flow chart. All right. So you start. So at the beginning of the program, you just start the program, and the first step is you take an input and store it in some variable A. You take an integer and store it in variable A, and then you take another integer. I think battery is low. Okay. Yeah. So you take another integer and store it in variable B, all right, and then you add these two values and store the output in another variable C. Okay, and then output that value in variable C. You print it either onto the monitor or through a printer on a paper, whatever it is, you output it in some way. Okay, right now we are not worried about the specific details of how it outputs. Okay, it reads two inputs. So this is the input portion, and then it adds them. This is the processing part, and then it outputs them. It adds them and stores them in a variable. So this is the processing part and the storage part, and it outputs the value of this variable. That is the output part. Okay, so just for a simple operation like addition, so many steps are there. Now imagine complex operations, right? It's like processing a video or anything. You can playing a game, right? Spreadsheet, analyzing a spreadsheet, sorting values, deleting duplicates, anything. So these are more complex tasks, and you need to give more complex or a longer sequence of commands to do those tasks, like finding the shortest path between one city and another city, right? These are all much more complex tasks. Okay, but whatever is the task, a computer basically just follows an algorithm, and you need to give that algorithm. Okay, and whatever is the algorithm, it is nothing but a sequence of steps, and all these steps are only of three types: take an input, process and store it, and give the output. All the steps in the algorithm can be categorized into these three types: input, processing, output. That's it. Okay. All right, so this is what we discussed. Computer is like a black box. Okay, so we give an input, computer takes that, it does some processing and throws the output to us. Okay, this input is in human understandable format, and the output is also in human understandable format, But what is happening inside a computer, we don't know. That's like a black box. Okay, right? That's what we use computers for, right? Like when you open a website, the URL you type is an input. The web page you get is the output. But how is it using that URL? How is it accessing that web page? How is it displaying it to you? How is it breaking down the content into pixels and showing them on your screen? If it is your mobile screen, it needs to display that web page in one way. If it is a desktop, it needs to display that web page in another way. So it's doing a lot of processing as to how to display this web page, right? So all that is black box to you. You don't know what it is doing. You are giving an input, you are getting an output. That's it. But it is doing a lot of processing at the back end, right? So this is what we will try to understand at a more fundamental level, not this example or that example, not about accessing web pages or not about finding the shortest path, not this or that example. We will work out many examples throughout this course, but the basic idea is for normal people who use computers, not necessarily those who are interested in becoming computer scientists, but for normal people, computer is a black box. Okay, but they can also interact with it by giving an input and getting an output. That's what happens, right? So now we are interested in opening up this black box and understanding what is happening inside that at a foundational level. Okay, once you understand the fundamentals, then building any building over these foundations will be easier. Okay, if your foundations are not weak, your building will fall at some point of time or other. Your building will be shaky. Okay, so don't focus on the building itself, focus on the foundations. Then you can build anything on your own. Okay, all right. So what is computer understandable format? Right, you see, input is human understandable format, output is in human understandable format, but whatever a human can understand, computer doesn't understand it directly. Because if I give a URL, it is in some maybe some language. It can be in English, it can be in Chinese, whatever it is. That computer doesn't understand directly. It only understands what? Bits. It understands only bits, electrical signals. So the letters which you give, they are not electrical signals themselves. They are not zeros and ones. So how does the computer understand them? It first needs to, there should be some translator which translates these alphabets or these letters into zeros and ones. And then a computer understands that. And then it does the processing over those zeros and ones. And then there should be another translator which translates these zeros and ones, output zeros and ones, back to some letters or whatever which we can understand. Okay? So the human understandable input is being translated into computer understandable zeros and ones, and the processing is happening at this level. Okay, so human understandable input is being translated into computer understandable zeros and ones, and the processing is happening at this level, and it is being translated back to human understandable output. Okay, so that is what is happening. So computer understands only zeros and ones or signals. All right. So what is 0 and 1? We discussed already. So you can think of 0 as off and 1 as on. Okay. So a binary 0 means off. No current is flowing through the light bulb, so it is off. Similarly, binary 1 means on. Here current flows through the light bulb to turn it on. Okay, as simple as this. So everything is nothing but electrical signals. Okay, but for our convenience, and also it so happens that these zeros and ones can be used in some computations. They become amicable to some logic. Okay, they become amicable to some operations. So that's actually surprising, right? So what is that logic? Does anyone know? Yeah? Boolean logic. So that is Boolean logic. So whatever you know of as Boolean arithmetic or Boolean logic, that is nothing but logic on zeros and ones. Okay? So although we are discussing electrical signals, if we represent them as zeros and ones, we can do some operations on them. And these operations can be used to perform more complex operations like arithmetic operations, addition, subtraction, multiplication, etc., and then much more complex operations, searching, sorting, or rendering some video, rendering some image, right? Or generating an image, generating a video. All these complex operations can be boiled down to binary operations. Okay, it so happens like that. So everything boils down to Boolean logic, Boolean arithmetic. Okay, so zeros and ones, 0 and 1, they are not just arbitrary symbols. Somehow they become amicable to Boolean logic, which in turn is the base for all high level operations that we are able to perform using a computer. Okay, so imagine if you have only one wire. Okay, so you have two options: either you pass current through it or you don't pass current through it. If you don't pass current through it, you can think of it as having a value 0. If you pass current through it, it's having a value 1. Okay, now, so given one wire, how many possibilities you have? 2. How many states? It can be in 2 states, on or off. Okay, now imagine you have 2 wires. So before I go to the slide, imagine you have 2 wires. Then how many total states you can be in? 4, right? So you can think of it as a table: wire 1, wire 2, right? 0, 0, 0, 1, 1, 0, 1, 1. Right? Wire 1 can be off, wire 2 can be off, wire 1 can be off, wire 2 can be on, wire 1 can be on, wire 2 can be off, both are on. 4 states, right? So, similarly for 3 wires, 8 states, right? So now you need to look at all these wires as a group. So this entire group can be in 8 different states. If it is 1 wire, it can be in 2 states. If it is 2 wires, that group can be in 4 states. If it is 3 wires, that group can be in 8 states, right? So if it is 4 wires, that group can be in 16 states. If it is k wires, that group can be in 2 power k states, right? As simple as that, right? 4 wires, 16 states. With more bits, you can represent more complex information. All right, so what do we mean by this? Now suppose I want to communicate some number with you, okay, but I don't want to send this number to you directly because someone may be eavesdropping. So I want to use a code. I will send a code to you. You will decode that to understand what number I want to communicate to you. Okay, so I assign a code to each number that I want to send. Fine. Now suppose, let's look at this 3 wires scenario. Now there are 8 different codes, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. So there are only 8 different possible states. So I will map a number to each state. These numbers need not be linear. I will just say 0, 0, 0 means 22, and 101 means 1035. Whatever it is, I have some 8 numbers, and I assign one of these codes for each of those numbers. So if I want to send 1035 to you, I will send 101 to you. So you will understand I want to communicate 1035 to you. Okay? But now, suppose if I want to communicate 9th number with you, how to do that? Using these 8 states, I can communicate 8 numbers with you. But if I want to communicate 9th number with you, then how to do that? Yeah? Can I do that with these 8 states? Yes or no? Yes? How?
So using arithmetic operations.
Using arithmetic operations.
But sir, we have not assigned arithmetic operations.
Sorry?
So, but we have not assigned plus minus, so we can't use it.
Yeah. So we have not assigned plus minus, so we can't. So let's forget operations yet. We are just dealing with data. We are not yet discussing how to manipulate this data. We just have data, plain data, fixed data. We are just assigning some codes to some numbers. We are not manipulating this. Okay? So assuming we don't have any manipulations, any operations, can I communicate 9th number with you using these 8 states?
So we can use two states as together.
We can use 2 states as together.
Then
No, we can't communicate a 9th number. That's it. So if we want to communicate 9th number, what should we do? Yes, we should use 4 wires. Okay? So if I use 4 wires, then how many total numbers I can communicate? 16. Right? So whether I want to communicate 9 different numbers or 10 different numbers or 16 different numbers, I have to have minimum 4 wires. So the moment I cross 8, I need to have minimum 4 wires. Even if you don't want to go up to 16, it doesn't matter. The moment you enter 9, you need 4 wires. Okay? So the more bits you have, the more data you can represent, the more information you can represent. Okay? Now if I want to represent, say, 50 different numbers, how many minimum wires I need? Yes? 6. Right? Why 6? 2 power 6 is 64. 2 power 5 is 32. So 32 will not be sufficient to represent 50 different numbers. So it should be between 32 and 64, minimum 64. The remaining spaces may go waste, but you need to have 6 wires. Right? You may want to stop at 50 different numbers. You may not use the remaining, you may not go up to 64. But you can't use just 5 wires to represent 50 different numbers. You have to use 6 wires. Okay? And as the numbers increase, the number of wires you need to use increases, and probably the amount of space you waste will also increase. Right? So I hope you got the point. Okay? So it's not necessary that you need to use every possible state. You may use only a portion of the new states, but all the remaining new states will go waste. But that's a trade-off you need to make. Otherwise you can't represent the data. Okay? So with more bits, you can represent more complex information. This you got, right? So now we have much more complex information. We will get to that later. So we have text, we have audio, we have video, we have images, right? And we have different kinds of signals. So lots of things. All this is data. All this is information. So more and more complex information. Video is more complex than audio and image, and audio or image is more complex than text, right? So to represent these different varieties of complex data, you need more and more space, right? You need more and more bits, more and more wires, that is more and more bits. So think of each bit as a wire. That bit can be 0 or 1. So the more bits you have, the more states you can be in. The more states you can be in, the more data you can map to. Right? Okay? So we'll come to that. But before that, let's look at something called the binary number system. Okay? Now even before understanding binary number system, it will be easier if you look at the decimal number system, because we all are familiar with that, right? So let's take a number like 1965. Okay? So we all know the units place, tens place, hundreds place, thousands place, and so on, right? So these place values matter a lot. Okay? Now units place gets that name. Can someone tell me why they are units place, tens place, hundreds place, thousands place? Why?
Because if you were to write it in expanded form, you'd write 1 into 1000 plus 9 into 100 plus 6.
Yeah. Yeah, that is the expanded form, right? But that expanded form comes after you know that see again language. Decimal means it has something to do with 10. Deca. So decimal number system means the base is number 10. You see, when I show you a number, technically, what number I am showing you until I also tell you the base. Technically, we assume that if I don't give a base, it is base 10. That is like taken for granted. But technically, I have to tell you, okay, 1965 in base 10, that is 1965. But if I change the base, this number changes to something else. Okay, so every number has a base. Alright, and we by default usually use base 10 system, that is decimal number system. Okay, but there is nothing sacrosanct about base 10 system. It's more convenient, that's a different thing. But you can do whatever you can do in base 10 system in any other number system. So binary number system is of base 2. Later you will also look at hexadecimal system, that is of base 6 or 16. 16, look at both the words, hexadecimal. It is 16, base 16. You will also look at octal number system, that is base 8. Sorry? 8, not 18, it's 8.
It doesn't have data, no?
Sorry?
So it doesn't have data, that's why octa only means it has.
Yes, it doesn't have deca. It's not like octadecimal system, it's just octal system. Okay, so it's 8. Okay, so these are all powers of 2. Binary, octal, hexadecimal, right? 10 is not a power of 2, that's something different, that's something special. That is more easy for humans to understand. Whereas for a computer, binary, octal, hexadecimal, these are easier to understand. Okay, because it understands only zeros and ones, those are only 2 values. Now you combine groups of zeros and ones to get octal system, hexadecimal system or whatever. Again, those systems are easier for a computer to understand. Okay? Alright. So now, like we said, a decimal number system is nothing but base 10 and hence each place value comes from the power of 10. So you start from right to left, you get 10 power 0, 10 power 1, 10 square, 10 cube and so on. So whatever digits you put in each of these places, you take each digit, multiply it with the place value and add up all these products. You get the final number. It so happens, decimal system is special because it so happens when you take each digit, multiply it with its place value and add up all these products, you will get back the same number. So you do 5 into 1 plus 6 into 10 plus 9 into 100 plus 1 into 1000, you will get back 1965. But if you take any representation in any other number system and if you do this, you will not get back the same number, you will get back a different representation in decimal basically. Okay, so suppose, okay, so this is decimal number system, right? Now in binary number system, what will be the place values? 2 power 0, 2 power 1, 2 square, 2 cube and so on. So you can think of it as units place, 2's place, then yeah, along the same. 4's place, 8's place, 16's place, 32's place, 64's place and so on. Right? So that's all. So in that sense, fundamentally, this is a number system, that is a number system, that's all. But fundamentally, the principle is same. Okay? And another interesting thing, how many digits, how many different digits you have in a decimal number system?
10, sir. 0, 1, 2.
10. 0 to 9. So you have 10 different digits in decimal number system. 0 to 9. Okay? How many different digits you have in the binary number system? 2. 0 and 1. Can you guess how many different digits you will have in an octal system? 8. 0 to 7. 0 to 7. Okay? 8 is not included. Like in decimal number system, 10 is not a digit. 10 is not included. You stop at 9. Okay? In a hexadecimal system, how many different digits you will have? 16. It will go from 0 to? Someone was saying 0 to 9. Yeah, 0 to 9 and then ABCD, that's fine. But the numbers are 0 to 15. Not digits, the numbers. Because we don't have a single digit representation for 10, 11, 12, etc., we replace those numbers with ABCD. Okay, but if we have a single digit representation, that's different. We don't have that. Okay, but each one of them can be used as a digit. Alright, and they have the value of say 10, 11, 12, 13, 15, 14, 15. Okay, so it goes from 0 to 15. Alright, suppose if I have a base, if I have a number system with base 27, then the digits go from 0 to 26, where the representation is different. You see, digit is an independent entity. You see, there are 100 people here. That 100 is an independent entity. Whether you write that 100 as 100 or HUNDRED or in any other script, 100 as an entity is independent. Okay? So, similarly, when I say 0 to 15, that number 15 is independent. Whether you write it as ABCD or whatever it is, or 1, 5, it doesn't matter. That is independent. Okay, you can think of it as a digit, you can think of it as a number or whatever it is. That value, the value of digits go from 0 to 15 in hexadecimal system. Similarly, if I have some system where the base is 27, the value of digits go from 0 to 26. The representation can vary. Instead of ABCD, I can use alpha, beta, gamma. It doesn't matter, right? But what I mean, the meaning is independent. The meaning is say number 11, number 15, whatever it is. Okay? Alright, so you will be given some reading material where you can read and understand some of these things. But right now let's look at just binary system. Alright, now let's just take this number 1100. Okay? Now this so-called 1100, you don't know what exactly it is representing until I tell you the base. If the base is 10, it is 1100, right? If the base is 2, it is 12, right? Why? You need to now convert this binary number into a decimal number. So how to do that? All you need to do is consider the place values. Here the place values are nothing but 1's place, 2's place, 4's place, 8's place, 16's place and so on. Okay? So take each digit in a particular place, multiply it with its place value. So 0 into 2 power 0 plus 0 into 2 power 1 plus 1 into 2 square plus 1 into 2 cube and so on. Here you don't have anything, so you need not worry. So finally what are you getting? 2 square plus 2 cube, right? 4 plus 8, 12. So that is the equivalent decimal representation of this binary number. Okay, so that is the value of this number basically. Alright, so whenever you look at a number, ask in what number system this is. Here, just because of the number system, the value is changing. Okay, if it is base 2, this number is not 1100, it is number 12. If it is base 10, this number will be 1100. If it is base 8, can you guess what number it will be? Yeah? 1000. Okay, I can't calculate 8 cube from the top of my head. What is 8 cube? 512. 512 plus 64. 576. That's all. So 1100 in octal system means number 576 in decimal system. Okay? That's all. So you can do it with any system, hexadecimal, octal, whatever it is. Okay? All right. Clear? Any doubts? So feel free to stop me in case you have any doubts. Okay? I can repeat. This is clear? Right? So depending on the number system, your base will change, and depending on your base, your place values will change. Alright? So all you need to do is, if you are given a number representation in a particular base, take each digit from the right, okay? Multiply it with the base power 0, then next digit, multiply it with base power 1, then next digit, multiply it with base square, and so on, and add up all these products. You will get the final result in decimal system. Okay? Fine. So this is another binary number 1001. Its equivalent decimal value is 9, right? Because 1 into 2 power 0 plus 0 into 2 power 1 plus 0 into 2 square plus 1 into 2 cube. So you can actually ignore the digits, the places with 0 values. Okay? Just take the places with value 1 and just add those place values. So 2 power 0 plus 2 cube, that is 1 plus 3, 1 plus 8, 9. That's all. Okay? Fine? Any doubts? Okay. Yeah, this is what we discussed. Okay. All right. Now let's imagine we have 32 wires. Okay. So what is the least number that you can store in 32 wires? Least number. Everything is 0. Everything is off. You can store 0. Right? When everything is on, is it 2 power 32?
Minus
2 plus 1. Okay, forget 32 this thing. Imagine you have only one wire. What is the minimum value? 0. What is the maximum value? 1. If you have 2 wires, what is the minimum value? 0. What is the maximum value? 2 wires. What is the total maximum value that you can represent? 6.
6. Yes, sir. 4 plus 2.
How 4 plus 2?
So 2. So the first one is 2 to the power.
See, finally all the representations that you are getting are only in zeros and ones. Okay? Simple way of understanding. Minimum value is when all are zeros. Maximum value is when all are ones. In between, if you have some zeros and ones, those will be in between. Okay? So if you have 2 wires, minimum value is 0, 0. If you have 2 wires, maximum value is 1, 1. So this binary number 1, 1 is what decimal number? 1 into 2 power 0 plus 1 into 2 power 1. That is what? 1 plus 2? 3. Right? So 1, 1 binary number means decimal number 3. Okay? Now, if I have 3 wires, what is the minimum value? 0. What is the maximum value? When all 3 are ones. So 1, 1, 1 in binary means what in decimal? Sorry? Sorry?
So it's gonna be just the maximum value is gonna be the summation of power.
Why is it too complicated? So far you understood, right?
Sir, the maximum value will be the summation of the 2 to the power 32 plus 2 to the power 31. Summation is like, so considering everyone is like 1,
Right.
so it will be 2 to the power 32 plus 2 to the power 33.
No, not. Your logic is correct, but it is not 2 power 32 plus. It is starting with 1. Think it's not 2 power 32 if you
So
have
2 to the
32.
power 31 plus 2 to the power 30 and
Exactly. And if you add up all those, what will you get?
that's the maximum values. So that I'll have to calculate that.
Yeah? Summation of 2 power n. Yeah, but it's not summation of 2 power n.
So it's the 2 to the power summation of n, sir, from 0 to 31.
Okay, so if you have 3 wires, this is the maximum number, right? All 3 are ones. Fine. So this is 2 power 0, 2 power 1, 2 square. So since these are all ones, you can just add them, right? So you will get what? 7. Fine. Now this, okay, so let's look at 4. So if you add all these, what will you get? 15. Right? 8 plus 4, 12, 12 plus 2, 14, 14 plus 1, 15. Okay? Now, if I have k wires, yeah, 2 power minus 1. This is the maximum value that I can represent using k wires or k bits. Okay? This so-called 7 is what? 2 cube minus 1. This so-called 15 is 2 power 4 minus 1. 4 wires, 2 power 4 minus 1. 3 wires, 2 cube minus 1. K wires, 2 power k minus 1 is the maximum value. So 32 wires, what is the maximum value? 2 power 32 minus 1. That's it. Clear? Okay, so minimum value is 0 and maximum value is 2 power 32 minus 1 when all are ones. And if you actually calculate this so-called 2 power 32 minus 1 number, you will get this number. So it's over 4 billion. So if you have 32 bits, you can represent these many different numbers. Right? If I want to store, if I want to add, if I want to multiply, whatever it is, if I want to deal with numbers up to a particular size, up to this number, I can deal with using 32 bits. But if I want to go beyond this number, then I need to add one more bit. But the problem is, in computer, you can't add arbitrary number of bits. If at all you are adding even 1 bit, you have to add 8 bits. You can't add 1 bit at a time. You have to add chunks of 8 bits at a time. So that is 1 byte. Okay? So suppose I have 4 bytes, which means how many bits I have? 32 bits. 4 into 8, 32 bits. So this so-called 32 wires is how many bytes? 4 bytes. Right? It's 4 bytes. Now, if I want to represent even one number larger than this, I have to add one more byte. Okay? I can't add a bit. I have to add a byte. So minimum 5 bytes I need. Right? Okay? Alright. Alright. Now, so right now, so far we understood that text can be, okay. You have another class? Okay. So, alright, I'll quickly wrap up. So, whatever data we have, we need to convert it to binary. Alright, we can have different kinds of data. It can be text, image, video, whatever it is. So, let's start with text. If I want to represent text in binary, what do you think can be different methods? Just take English. Okay? Yeah?
Depending on what position each alphabet.
Mapping, yeah. So, how do you map? Yeah, yeah. Any other? Any other? Yeah, fine. But what is ASCII value? What is the concept? No, not full form. What is the concept of ASCII value? Yeah. So you see, if it is a decimal number, it's easy. We can map it to some binary representation. Actually, in this class, I just showed you one way of conversion, binary to decimal. I didn't show you the other way. Decimal to binary, I didn't show you. This you need to look up. Okay? So, there the algorithm is slightly different. But, given a number, now you understand how to represent it in binary. Okay? You just need to divide it with 2 repeatedly. And then whatever reminders you get, you just need to list them in reverse. You will get the binary representation. Simply, that's how you convert decimal to binary. Okay? So, any number, we can represent it binary. Okay? But if you have some data which is non-numeric, it can be text, it can be image, whatever it is. So, how do you convert it to binary? use the algorithm to convert that decimal number to binary. Right? As simple as that. So such a be done for text. Okay? It is a standard mapping that is called ASCII. So this so-called ASCII mapping looks like this. Okay? So all the keys on your keyboard, some of them are printable, some of them are non-printable, some of them are visible, some of them are non-visible. Examples of non-visible keystrokes, what?
Enter space also.
Enter. Space is in some sense visible. Delete. Right? Yeah, control. These are all keystrokes, right? So even these keystrokes, every keystroke is given a number, and that number has some decimal value, and you can convert it to binary, octal, hexadecimal. So this chart gives you the decimal value and its equivalent hexadecimal value. Okay, not the binary value. You can again convert this hexadecimal to binary or whatever. Any number system you can convert from one to the other. Okay, fine. So all the digits which we use 0 to 9 and all the alphabets which we use A to Z, small letters and then capital letters, all of them have different values. They are given different decimal values, and then you can convert this decimal to binary. Okay, but this ASCII, it uses only 7 bits. So using 7 bits, how many different values you can represent? You see, usually people get confused here. When I have k wires, the minimum value is 0, the maximum value is 2 power k minus 1. But the total number of different values are 2 power k, right? It is 0 to 2 power k minus 1, not 1 to 2 power k minus 1. So if you count 0 as well, the total number of values are 2 power k. Okay? So if you have 7 bits, the total different values that you can represent are 2 power 7. The minimum value is 0. The maximum value is 2 power 7 minus 1. So the range is 0 to 2 power 7 minus 1, but the number of different values are 2 power 7. Okay? So 128 different characters are captured here. Alright? And then we have extended ASCII, some more, some like punctuation symbols, or some Western European languages, they have some accent, right, on some letters. Yeah.
So like in French also.
Sorry?
So in French like that,
Yeah. French, like in French. Yeah. So those can also be captured using one more bit. So now how many different values you can capture? Using 8 bits? 2 power 8. Okay. So you basically double the total number of different characters that you can store. Using 7 bits you can store 2 power 7 different characters, but using 8 bits you can store 2 power 8 different characters. Okay. But later people found that even this is not sufficient, because we have non-English or non-European languages like whatever Indian languages, Chinese, Japanese, all these things. So it is extended to something called Unicode. Okay, it can store all the languages, all the symbols in this world. Okay, so that uses basically minimum 4 bytes or 32 bits, right? So something like that. And so we can store emojis also, or punctuation symbols, or non-English letters, all those things. Okay, so basically we are taking a non-numeric character and mapping it to a number and converting that number to binary. That's all we are doing. So text or binary, it is easy to represent text in binary. Okay, binary is easy. So you take each of these characters, each character has an ASCII value. You convert that ASCII value to binary. That is how it is stored in the computer. Okay, so this is so we just stopped at text here. We will look at other examples in the next class. Okay.